Welcome back to the Deep Dive. Today we're tackling, well, what's often called the Swiss Army knife of data handling in Python, the list.
It really is. It's got a tool for almost everything.
And for this, we've got a whole stack of detailed technical notes, some programming exercises, and our mission today is to get you, our listener, way beyond just the basics. We want to equip you with a real mastery. So we'll cover how lists are built, how they play with other types like strings, and, maybe most importantly, how they handle memory.
Yeah, that memory part is where it gets really interesting.
It is.
So to start, what is a Python list? Fundamentally, it's a type of sequence, a container.
An ordered collection of items.
Yeah, exactly, an ordered collection. Now, you might have seen that with strings, right? They're an ordered collection of characters.
Sure.
But the crucial difference, the thing that makes lists so powerful, is that the elements can be of any type. Numbers, strings, other lists, you can mix and match them all in one place.
That's the source of their power right there, that flexibility. So let's start at square one. Literally. The square brackets.
Yep. Just down signal. That's the visual signal. You see those? You're looking at a list.
And getting things out of it. Accessing elements.
It's the same syntax as strings, the same muscle memory. You just use the index operator, so list name index.
Easy enough. And there are a couple of essential utilities that go along with that.
Right, like how many things are in my list. For that, you just use the len function, len list object.
Which is great.
Yeah.
But what if you have a massive list and you just want to know if one specific thing is in there without having to check every single item yourself?
Yeah, you definitely don't want to loop through a million items. That's why the Boolean operators in and not in are so indispensable.
They just give you a true or false.
Instantly. It's incredibly efficient. It saves a huge amount of computational effort.
And speaking of going through items, traversal. Lists are built for that, aren't they?
Oh, absolutely. I mean, they're sequences, so they're designed to be walked through one item at a time. You can use a for loop, a while loop, whatever fits. That flexibility is just fundamental.
Okay, so we know how to build them and look inside, but the real power kicks in when you start, well, manipulating them. Let's talk about the operators.
The plus and the tis.
Right, and they don't do what a beginner might think.
Yeah.
The plus sign isn't for math here.
Not at all. In the list world, it means concatenation. It just, joins two lists together to produce a brand new, bigger one.
And the star operator.
Ah.
The asterisk.
That's repetition. It just repeats the elements of the list a certain number of times. So 1, 2 times 3 becomes 1, 2, 1, 2, 1, 2. It's a neat little shortcut.
And building on that, slicing. This is something that works exactly the same as it does with strings.
A match made in heaven, really. The syntax, start index, end index step is completely universal here.
We just have to remember that one critical detail.
Yes, the start index is inclusive.
But the end index is exclusive.
It is. It goes up to, but does not include that final index. Getting that wrong is the source of so many off-by-one errors.
Okay, so now we get to the big one, the central difference between lists and something like a string. Lists are mutable.
That is the game changer.
Yep.
It is. Mutability means you can change, replace, update, whatever you want to call it.
Yeah.
You can modify the elements in place.
You don't have to create a whole new object.
Exactly. You just reach into the existing list and swap something out.
Now, for modification, the source materials specifically call out the del statement for deleting things. Why that instead of a method like .pop?
That's a great question. So .pop is useful when you want to move an item and use it for something else. It removes it and hands it back to you.
Okay.
And looks for the first item with a certain value. But del is different. It's Python's direct command to delete by index. If you know exactly where the item is that you want to get rid of and you don't need it back, del is the cleanest, most direct way to do it.
It's more of a language command than just a list method. So this mutability, this flexibility, it's amazing. But it also creates a huge challenge when you try to copy or share data. Which brings us to the deep part of the dive, memory and references.
Right, because with an immutable type, like a string, if you use the equal sign to assign it to a new variable, you eventually get a new copy. But with a list,
if you just do list A equal list in B,
you do not get two independent lists.
No, you get a shallow copy. Or more accurately, you get an alias.
You get an alias, exactly. All you've done is copy the reference, the pointer. Both variables now point to the very same object in memory. I can't tell you how many hours I lost to that when I was starting out.
It's like you think you photocopied a document, but all you've really done is create a second shortcut on your desktop that opens the same master Google Doc.
That is the perfect analogy. And if you edit through one shortcut,
You're editing the one and only document, everyone sees the changes.
Yep. And the notes are smart to suggest visualizing this using something like pythontutor.com, where it actually draws the boxes and arrows. That's the aha moment for so many people.
So if we're in our code and we suspect this is happening, how do we test for it? How do we know if two variables are pointing to the exact same thing?
For that, Python gives us a special operator, because is.
Not the double equal sign.
No double equals. That just checks if the values inside are the same. Is checks if they're the very same object in memory. If list A is, list B is true, they are aliases. It's a critical debugging tool.
Okay, so if the standard equal sign creates this risky alias situation, how do we make a real copy?
Now we get to the solution. Shallow copy versus deep copy.
Great.
A shallow copy creates a new list. So the top level container is independent. You can change elements on that top level, but, and this is a big but, if your list contains other mutable objects, like other lists.
Like a 2D list.
A list of lists. Exactly. A shallow copy only copies the references to those nested lists. So if you change a nested list in your copy, you're also changing it in the original.
Wow, so it only solves half the problem.
It's a partially independent copy. If you want total, absolute independence all the way down, no matter how nested it is, you have to do a deep copy. And for that, you usually have to import Python's copy library.
So that's the key. If you have a simple list of numbers, shallow is probably fine. But for a list of lists or a list of other complex objects, you have to go deep.
You must, if you want to guarantee they stay separate.
And this whole mechanism, this idea of passing around references instead of data, has a huge impact on functions.
A massive impact. Because lists are mutable, they are passed by reference into functions.
Meaning the function gets the memory address of my original list, not a brand new copy of it.
That's it. So if that function then, say, appends an item or sorts the list, it is changing your original list outside of the function. This is so different from how numbers or strings are handled.
Understanding that difference is,
Yeah.
that's the mark of moving from a novice to someone who can write robust code. You have to intentionally protect your data.
You do.
Okay, now that we've got our heads around the memory model, let's talk applications. Connecting lists to other data types. The relationship with strings is a big one.
Oh, it's critical for data processing. You get a line from a file, it's just one long string. You use the .split method, and suddenly you have a list of words or values you can actually work with.
And then the reverse is using that join.
Yep. You take your list of strings, and you use a delimiter string, like a comma, to join them all back together into a single text unit. That round trip is the foundation of so much data work.
We also talked about converting lists into tuples and then back again. Why would you do that?
For safety, it comes back to mutability. Tuples are immutable, they can't be changed. So if you have some data you need to sort or temporarily modify, you can cast the tuple to a list.
Do your work.
Do your work, and then cast it back to a tuple to lock it down again. You get the flexibility when you need it and the safety when you don't.
And for a really concrete application, the notes bring up using lists for math, specifically to represent vectors.
It's a perfect fit. The exercise mentioned is writing a function, add vectors, that takes two lists of numbers.
And it returns a new list where each element is the sum of the corresponding elements from the input lists.
Right. And to do that, you just iterate through them together using their index, adding U plus V, and putting the result into a new list. It's a really clean demonstration of lists as these ordered mathematical containers.
And they scale up from there, right? To handle more complex problems like grids.
Oh, yeah. The next level is the 2D list, a list of lists. That lets you represent any kind of table or grid. Think about a Sudoku checker.
You need to check rows, columns, and the little 3x3 squares.
Exactly. And a 2D list maps perfectly to that. The first index is your row, the second is your column. It's the natural way to model that kind of problem.
That makes sense. Any kind of board game, data matrix, anything like that.
It's essential. And the last example here is also really clever, using a list of tuples for complex sorting.
Like the roll call problem.
Right. Imagine you have to sort students first by their grade and then alphabetically by name. You can store each student as a tuple, like grade, name. The tuple itself is immutable, so the record is safe. But you put all those tuples into a list.
And then you can use the list's powerful sorting methods on that complex data.
Precisely. You get the best of both worlds.
Wow. Okay, so we've really gone from the simple square brackets through operators and slicing, all the way into the deep end with mutability and how lists affect program memory.
It's a big topic.
It is, but I think you, the listener, now have the tools to use lists not just as simple containers, but for really complex tasks like vector math, solving grid puzzles, and managing complex data.
You've got the toolkit. And more importantly, you understand the risks that come with that power. We spent a lot of time on mutability and passing by reference for a reason.
Which brings us to our final thought.
Right. So I want you to think about this. You're in a real production system. You've got a list that holds mission-critical data. Maybe it's security settings for your application. And you need to pass that list to some helper function to, I don't know, run a quick diagnostic check. What do you do?
Well, it's the safest choice.
Exactly. Do you take the performance hit, use the extra memory, and make a full, safe, deep copy to guarantee total separation? Or do you opt for a faster, shallow copy and just hope that function doesn't touch any nested data it shouldn't?
It's a trade-off.
It's always a trade-off between performance, memory, and data integrity. That's the essential challenge and the responsibility that comes with mastering mutable structures, something to explore for yourself.